context. If I were to say to you, hey, it's 0 degrees outside today, is it possible? No. There's actually not enough context in that data to understand what I'm saying. Because we want to know what the actual degree measurement is. Is it Celsius, so 0 degrees Celsius, or is it 0 degrees Fahrenheit? Or hey, is it 0 degrees Kelvin? Hopefully it's not 0 degrees Kelvin,
Hello.
otherwise that's basically impossibly cold. Okay, so context, understanding the data, what it's actually representing, whether the price of something represents the price that a consumer pays or the price that the company pays, etc., is also extremely important to your overall data quality. And so now we should have a thorough understanding of overall data quality, completeness, uniqueness, timeliness, accuracy, and context understanding. Coming up next, we're going to briefly discuss big data and the key factors that differentiate it from just normal data sources. I'll see you in the next lecture. Welcome back, everyone, to this brief lecture on big data. All the previous data quality features still apply, just now on a much larger scale. We can think of this as the 4 V's of big data: volume, variety, veracity, and velocity. Volume basically just means how much space is being taken by this data. We're talking about gigabytes, terabytes, or petabytes. There's a different technology set for each scale. And we're typically talking about big data once you reach enough data that it can no longer fit on your desktop or laptop's RAM. That is the random access memory that's on your computer. Laptops generally range anywhere between 8 to 16 gigabytes of RAM, which actually means that you can have pretty large data sets fit entirely on your laptop or desktop's RAM memory. Now, if you're starting to get beyond what can fit on RAM, then you moved on to probably something that needs to be distributed on a cloud service such as Amazon Web Services, and you're starting to enter big data territory. Then there's variety, which is the type of data. So, at a much larger scale, variety tends to amplify the problems of different types of data. So, unstructured data has its own issues at larger scales, and structured data also will then have to be formatted correctly in order to correctly line up if it's distributed across multiple computers, since it's such a large structure table. Then we have the veracity of the data, which is just the general quality and accuracy of the data. Basically, a lot of the features that we previously talked about in the previous lecture. And then there's the velocity of your data. That's the frequency and scale of incoming data. Typically, the reason you have large or big data is because you have multiple in-sources of data coming in at a very high velocity. So you can imagine a very large service such as Google or Facebook has big data because we have a high velocity of data. So we have tons of users and we're logging a lot of their activities as data points. So we have a high frequency and large scale of incoming data. Okay, so for this section on data, we've learned the key components of good data quality, and we've also learned what differentiates data from big data. Thanks, and I'll see you at the next lecture. As we already know, data in its raw format can be overwhelming and difficult to comprehend right away. We've learned about some basic statistics that can give us a high-level overview of some data features. But there are also a variety of visualization techniques we can employ in order to build an intuition and deeper understanding of our data. In this section of the course, we're going to be discussing a variety of different visualizations. Let's get started. I'll see you in the next lecture. Welcome everyone to the section on visualizing data. We're going to discuss a few key plot types and what you may be using them for. And we're going to separate these plot types into three distinct categories: relational plots, categorical plots, and distribution plots. So we'll have 3 subsequent lectures that discuss these type of plots. Let's get started. One of the most common plot types are relational plots. And relational plots allow us to relate or compare 2 different features in our data set. They also allow us to then add in even more information from other features using things like color and size. The first plot, that is a relational plot, is probably a plot you're already familiar with, which is the scatter plot. This classic plot type is meant to convey a relationship between 2 continuous features. It could also use color and shapes to add more feature information, and we'll see some examples of that. Points are plotted where the features meet up for any particular row instance. So in these several examples we're going to be showing you, we have a data set about tips left after various sized parties for various meals. So we have a bunch of data where people visited a restaurant, they paid their total bill, left some sort of tips, and then we also have a bunch of information about the party that had that meal, whether it was lunch or dinner, whether it was a male or female leaving the tip, etc. So we've also included information about that time of day and meal type. So let's first see a very simple scatter plot. And here we have a relational plot, which is a scatter plot. And on the y-axis, we have tip, and on the x-axis, we have total bill. So right off the bat, we can see some sort of correlation or relationship between total bill and tip. It seems that as total bill increases, so does the tip. And in general, that makes sense. Tip is usually a percentage of your total bill, so it would make sense that as one grows larger, the other grows larger as well. But we can also see some outliers. For example, we can see around the x-axis $10 total bill mark that someone has left around a $5 tip, so a 50% tip on their $10 total bill. Not too shabby. So we have this scatter plot, but we can add more information. So far, we're only showing 2 dimensions or 2 features, total bill and tip. What we could do is use color to add a new feature of time. So here we can show lunch versus dinner. And from this plot, it doesn't look like there's any clear distinction between lunch and dinner, except for the fact that we have way more instances of dinner than we do of lunch. We can't really say, just from this plot, if there's a distinct relationship between total bill versus tip difference for lunch versus dinner. It just looks like our data set itself has a lot more dinner instances. Now, if we wanted to, we could add even more data by using not just color, but also shape. So here we have the day of the week, Thursday, Friday, Saturday, and Sunday, as their own distinct colors. And then we also have lunch versus dinner as actual shapes, a circle versus an X. So here, just on this flat plot, we're actually showing 4 features of data. We're showing the total bill, the tip, the day of the week, and whether it was lunch or dinner. And this is where you can convey a lot of information. Keep in mind that if you're going to be printing out these sort of plots in black and white, the day, Thursday, Friday, Saturday, and Sunday, that is dependent on color, will then no longer be useful because it'll be in grayscale and it'll be very hard to determine the shade of gray that matches along the plot. So keep in mind, whenever you're using color for your plots, you want to make sure
that this will never be printed out in grayscale, otherwise that information will be lost. Now we can also use size in conjunction with color. So here we can see the size of the actual party, so if it was 1 person, 2 people, 3 people, or 6 people, and we've also corresponded that size to color. So technically right now, the size of the dot or circle and the color of that circle are actually trying to show the same information. This allows readers to be able to easily see size, not just based on the size of the circle, but also on the color. So we've joined the fact that as the color gets darker and the circle gets larger, that means the size of people that actually had that meal, there was more people there. And then as the size of the party gets smaller and the color gets lighter, then we have less people. So again, we can see a clear relationship. And what's interesting about this is we notice a general trend that the colors get darker as you go up towards the right-hand corner, and the circles tend to get larger, which makes sense. If you have a larger total bill, it's more likely that you had more people, because it'd be unusual for 1 person to be able to spend $50 by themselves when it looks like on average 1 person is spending between $10 and $20. Now let's move on to a line plot. This is again a classic plot type that you've probably seen before, which is going to convey relationships between 2 continuous features. And typically the x-axis conveys some sort of start point. So this plot type is commonly used with timestamps or time series data. Essentially, all it really is, it's a scatter plot with the points connected. So let's see an example of this. Here, we have a data set which starts with some sort of timestamp at 0, and it continues on. And then there's different events that occur, and we have some sort of signal value on the y-axis. So we typically, for line plots, have some sort of continuous x-axis that has an actual starting point at 0 or whatever number it happens to be. So that's why it's really common to see this with time series. And then we put out points and we just connect those points with a line. So you've probably seen this sort of plot before, very easy to understand. Now typically, if you don't want to actually show the individual points, you can just smooth this out to be other lines. Here we see another set of series, and then we have time series again, and there's way more lines in this one. But here we can see now there are no longer individual points. So basic line plot, you've probably definitely seen this before. Coming up next, we're going to discuss categorical plots. Welcome back, everyone. In this lecture, we're going to continue our discussion with categorical plots. So far, we've seen mostly plots that have continuous data on both x and y axis. Let's see how we can visualize categories. We'll be discussing a count plot, a bar plot, and then, before we actually discuss box plots in details, we'll have a discussion on quartiles. So let's start off with the basics. First off, the count plot, which is again probably a plot you've seen before that's very basic. What a count plot does is it simply shows the counts of observations in each categorical bin using bars. A count plot, again, can be thought of as a histogram across a categorical instead of quantitative or continuous variable. So let's see what this actually looks like. Here you can see some data from the Titanic, and it's just counting the number of instances per category. So here we can see there's a little over 200 instances of first-class passengers. So the count is essentially just translating how many people are actually in each class, first class, second class, and third class. Again, this is just a count. It's literally counting up the number of rows or instances. Now for count plots, you could then also add in another feature by separating out these bars along another category. So for example, we could separate this out based off of who they were. Were they a man, a woman, or a child? So now we see 9 bars in total. The y-axis hasn't changed. We're still showing count. And if you were then to stack these actual bars on top of each other, the count should show up the same as it was before in the previous plot. So again, here we're seeing now the feature of the class, how many people were in each class, and then separated by another category, man, woman, and child. And often you'll also see these stacked on top of each other instead of side by side. I would prefer to see them side by side as shown here because it's easier to compare when they're side by side instead of stacked on top of each other. So I can clearly see that the third class had way more men as a ratio compared to women and children than the second class did. Okay, so now let's move on to a very similar plot called the bar plot. A bar plot represents an estimate of central tendency for a numeric variable with the height of each rectangle and provides some indication of the uncertainty around that estimate using error bars. So what this actually looks like, if we go back to our tips example, is something like this. Notice that we're not actually now counting the number of instances. Instead, on the x-axis, we've chosen some category, such as the day of the week that this person went to have their meal. And then on the y-axis, we're showing the average, or some sort of measure of central tendency. Almost always it's going to be the mean here. So I can see the average of the total bill per weekday. And just off this plot, I can see that I have a higher average on Saturday and Sunday than on Thursday and Friday, which kind of makes sense. If you're heading towards the weekend, people going out for meals are likely tend to splurge a little more. And those black bars on top of the Thursday, Friday, Saturday, and Sunday bar plot, those are representative of the standard deviation. So we see the actual average along the y-axis, the top of the bar, and then that black line represents the standard deviation, so plus or minus a certain value. Okay, so now we understand count plots and bar plots. And just like count plots, we could also add in one more feature. So here we can see the sex, male versus female, and then compare that throughout the days. So you can always add in more information using multiple bars. However, you should always try to make your plots as readable as possible. Moving along, we have the box plot. And this is probably the most complicated plot that we're going to see throughout this discussion. And a box plot, also called a box and whisker plot, shows the distribution of quantitative data in a way that facilitates comparisons between variables or across levels of a categorical variable. And to truly understand the box plot, you need to understand what a quartile is and what an interquartile range or IQR is. So we're going to take kind of a brief aside in order to have that discussion, but I first want to show you just a couple of examples of what a box plot can look like. So again, the box plot, what it's going to do is it's going to show the quartiles of the data set, while the whiskers extend to show the rest of the distribution, except for points that are determined to be outliers using a method that is a function of the interquartile range. And we'll show this mathematically in just a little bit. But a couple of examples of box plots. Again, here we're showing box plots with the x-axis being the category of day and the y-axis being total bill. And what this is essentially showing us is the distribution of the total bill for Thursday, Friday, Saturday, and Sunday. And if we wanted to, we can add in a new feature, such as whether or not this person was a smoker, if that feature happened to be in our data set. So yes or no smoker, and then you can put box plots next to each other. But let's go ahead and discuss how these whiskers are actually calculated, what that central box represents, and what that line in the middle of the box represents. To do this, we're going to talk about interquartile range. So we're going to be discussing quartiles and IQR, which stands for interquartile range. So one way to describe data is through what we just mentioned, quartiles and the IQR, or interquartile range. What's really advantageous about quartiles is that every single data point is considered. There's no aggregation like we previously saw with means or variance. So let's show you how to actually calculate the quartile. Let's consider the following series of 20 values here. What we end up doing is a couple of steps. Step one, we divide the series in half, which is essentially the same thing as finding the median value in the series. Remember, the median is that middle point in the series. Then step two is we divide each of these sub-series in half as well. So now I have 3 lines there. One of them in the middle divides everything in half, and then we have those other 2 lines on the outside that actually divide those sub-series in half. Then these 3 lines actually become the quartiles. Because remember, in order to chop up things into quarters, or 25% each, then we need 3 lines. So we have the first quartile, the second quartile, otherwise known as the median, and the third quartile. So what this does is it splits up our data set into 4 same-sized buckets. So the first quartile, the actual value there, is going to be the value that splits up that lower half in half. So in that case, that's going to be the value between 13 and 15, which is 14. The second quartile, or median, is what splits the entire data set in half, which in this case is between 21 and 23, so that's 22. And then the third quartile is going to be 35, essentially what splits the upper half in half again. So 35 is in between 34 and 36 there. So again, notice we have three quartile values, those three lines. So now that we have these quartiles, we can actually plot them out using what's known as a box plot. So here we see a box plot, and we also see the actual individual points right below it. And essentially what the box plot shows is the actual distribution of your data. So we have what is known as the box in the center, and then what is also known as whiskers extending out from that box. Keep in mind that quartile ranges themselves are seldom the same size. Essentially what this is showing you is from the minimum to the first quartile value, then that inside box, essentially the shaded region of that rectangular box, that's the middle half of your data. So that's the 50% of all your points that are right in the middle of your data, from quartile 1 to quartile 3. And then in order to understand the actual distribution of that middle set, what we end up doing is we draw a line, a vertical line inside of that rectangle or inside of that box at the median. And then we have another whisker extending all the way to that max. So let's actually talk about fences and outliers and how you deal with these. Specifically, how would you just actually calculate what an outlier is? A very common practice is to actually set what's known as a fence that is 1.5 times the width of the IQR. Anything outside the fence is then an outlier. So IQR is the interquartile range, which we're going to discuss in just a second of how to actually calculate it. Keep in mind, what's really nice about this approach is that your outliers are determined by the actual data itself, not some sort of arbitrary percentage of 5% below the max or something like that. Instead, you're actually using the distribution itself of your data set to define what an outlier is. So this is best seen visually. First, we have the IQR, or interquartile range. And all that means is the actual distance between Q1 and Q3, or quartile 1 and quartile 3, which is just the value of quartile 3 minus the value of quartile 1. So 35 minus 14. So you take that interquartile range, remember that's the actual just length of that box, and then you're going to times it by 1.5. And we essentially say that anything outside of that range is then considered an outlier. So in this set, we have the number 60, and that's actually not considered an outlier, but something outside of the 1.5 times IQR range would be considered an outlier. So for example, 70 would be an outlier in the specific data set. So here, let's go ahead and add in 70 to that data set, and notice that it's now falling outside of that fence that we created at 1.5 times IQR. So here 70 is a true outlier. And this is a nice standardized way of deciding what is an outlier in your data set and then what is not an outlier. And then depending on the context of whatever business decision you're trying to do, it may make sense to just throw away outliers, or it may make sense to keep them and examine them more closely. Now, when you're drawing box plots, keep in mind the whiskers are brought inward to the outermost values inside the fence. All right, you should now have an understanding of quartiles and how to calculate them, as well as a basic understanding of how you can visualize quartiles using a box plot. Welcome back, everyone. In this lecture, we're going to discuss distribution plots, specifically a histogram. A histogram is an accurate representation of the distribution of numerical data. It differs from a bar graph in the sense that a bar graph actually relates two variables. Recall that in a bar graph, we chose a category feature for our x-axis and another continuous feature for our y-axis. A histogram actually only relates one variable. The histogram reveals the distribution of a single continuous feature by counting occurrences and then assigning them to bins. So let's see a couple examples of this. If we take a look back at our tips data set, here we're showing a histogram of the total bill. So we've chosen one single continuous feature and put it along the x-axis. And then what we do is we decide on a number of bins to show the distribution of the data. And then all the y-axis is showing is the number of occurrences for that particular bin range. So we can see that it looks like most total bills on average are in between somewhere like around $10 to $20 because those have the highest number of occurrences. So all the y-axis is showing is the count or number of occurrences. Now you can edit a histogram by deciding on having more or less bins. So if we choose to have more bins, we're going to get more detail around the actual distribution because then we have a less width of the bin or a narrower bin size. So notice here we increase the number of bins, meaning that the actual bins themselves are going to be skinnier. So we can see the underlying distribution in more detail. You should be careful, however, to not choose too many bins, otherwise you'll end up with certain bins that are empty because there are no particular occurrences for that range of values. So here we can see choosing many more bins to start seeing a smaller bin size, and now you can see that there are certain total bills where there was 0 occurrences or 0 counts for a particular range. So here we can see between $40 and $50, there's certain amounts of money that were just never spent, so the histogram is blank there or there is no actual bar count. Now, conversely, if you choose too small a value for number of bins, you're not actually going to see the distribution. So here we're showing the same data now in 4 bins, and we're not actually able to see the true distribution. So a good rule of thumb is to actually choose something like 20 bins and then work up or down from there, depending on the size of your data and the range of values. Out of these histograms that we've seen here, I would recommend choosing this one as probably the best representation of the data. Now, as a quick point, you can actually join plot types. So we can create more complex plots by combining different plot types that we've already seen. So here we can see a combination of a scatter plot and a histogram. So the way to read this is we can see the scatter plot of total bill versus tip, and then what's nice about this is we can also visualize the actual histogram for total bill and tip on their corresponding x and y axis. And notice here how the 2 lines, one on the very top and one all the way to the right, they're actually not connected or joined to the total bill and tip lines. That's because they're technically not really related to those particular axes. Instead, they're their own histograms showing you the distribution of total bill and then separately the distribution of tip. So you can convey a lot of information by continuing to join these different plot types that we've already discussed. And there are even more complex plots on top of this. For example, let's say for total bill and tip, you notice that we have a lot of points that are potentially stacked on top of each other. One way to try to fix this problem is by using what's known as a hex bin plot. Essentially, you would just divide this area up into hexagons and then shade the hexagons depending on how many points fell upon that particular hexagon area. So we can convert it to look something like this, and essentially the darker the hexagon, that means there were more points in that particular area. So this is one way to be able to visualize when you have so many points that are scatter plot. Essentially makes no more sense because you have so many points stacked on top of each other. And this is known as a hex bin plot or a hexagonal bin plot. All right. I hope now you have a full understanding of the different types of visualizations that are available to us with our data sets and how we've been able to combine ideas from data quality and statistics. Thanks, and we'll see you at the next lecture. Welcome back, everyone. Now that we understand the visualization of data concepts, let's go ahead and explore some real-world applications. So, in this lecture, we're going to quickly explore some general real-world cases you may want to use for visualization of data, things to keep in mind for your own applications, and then a specific real-world business case. So, different general real-world cases that you may want to be using data visualization for is typically for judging comparisons between groups, especially if you have lots of data points within each group. You can aggregate them easily and then visualize the comparison. You can also reveal strong historical trends using data visualization, as well as just in general understanding large numerical datasets through aggregation techniques. Things to keep in mind when you're working with your own data visualization problems is, what is the story you're trying to tell? Often, you're using data visualization in conjunction with a presentation to some other people. So you want to keep in mind before you even start the visualization is, what's the story you're really trying to tell? As an alternative, if you're really just using data visualization to explore your own data and the visualization is just for yourself, you should always ask yourself, what's the question you're trying to answer before you even begin data visualization? And you can always explore other visualizations and other resources and allow the data to inform your choice of what data visualization to use. As far as a real-world business example, the 538 news site was started by statistician Nate Silver to explore topics such as politics, sports, and economics with a statistical approach. And data visualization plays a huge role in their stories. So what I would recommend you do is go to www.538.com and specifically explore their political visualizations. Regardless of how you feel about politics, you should really start looking at their visualizations and think about their use of color, scale, chart types, and what's the story they're trying to get across. You should look at the headline of the story and see how that relates to the data visualization. Okay, I hope you have fun exploring that website. It's a really great tool to get an idea of what's possible through data visualization. Thanks, and we'll see you at the next lecture. Welcome to the machine learning process section. We've come a long way in our understanding of data, statistics, and visualization. Now it's time to apply that knowledge in conjunction with machine learning techniques. In this section of the course, we're going to cover the general machine learning process, as well as discussing supervised versus unsupervised learning techniques. I'll see you at the next lecture. Welcome back, everyone. In this lecture, we're going to have an overview of the machine learning process. So before we dive into any specific algorithm, let's work on understanding the general machine learning process we're going to be using. The first specific case of machine learning we're going to be conducting and learning about is known as supervised learning. Later on in this course, we'll discuss unsupervised learning methods like clustering and dimensionality reduction. Because different students have different backgrounds in math, We're going to keep the mathematics behind the machine learning algorithms themselves on the lighter side and really try to just understand an intuition behind the way they're working. If you are interested in the mathematics behind these algorithms, a really great textbook on general machine learning is An Introduction to Statistical Learning by Gareth James. I would highly recommend it as a companion book if you are interested in learning more about the details behind the way these algorithms work. It's freely available online from the authors. Simply Google search the title of the book and the first link should take you there. So first off, what is machine learning? Machine learning is a method of data analysis that automates analytical model building. Using algorithms that iteratively learn from data, machine learning allows computers to find hidden insights without being explicitly programmed where to look. Now, machine learning has a wide variety of use cases. Everything from fraud detection, for example, if you've ever used your credit card overseas and then have been alerted to fraud based off your previous transaction patterns, that is a machine learning algorithm that is trying to learn based off of previous history what is likely to be a fraud transaction versus a legitimate transaction. But there's all kinds of applications such as prediction of equipment failures, financial models, intrusion detection, recommendation engines such as on Netflix or Amazon Shopping, text sentiment analysis, pattern and image recognition, email spam filtering, and much, much more. So let's talk about supervised learning. Supervised learning algorithms are trained using labeled examples. Labeled examples means we have historical data that we already have the label for. So that means we have labeled examples such as an input or the desired output is known. For example, a picture could have a category label such as either dog or cat. So the actual data itself would be the image of a dog or a cat, and we have a corresponding label that actually labels the image whether or not the computer is seeing a dog or a cat. So someone has manually gone in and labeled these dog or cat. The learning algorithm then receives a set of inputs along with the corresponding correct outputs. And the algorithm itself is going to learn by comparing its actual output with the correct outputs to find errors. It then modifies the model accordingly. Supervised learning is commonly used in applications where historical data predicts likely future events. Just like that previous credit card example, we have historical information on your transaction history, such as always performing credit card transactions in certain areas of the United States. That's why if the bank suddenly sees a transaction that it seems to be like an outlier based off your previous history, such as a transaction suddenly happening in Africa when you've never really been there or you haven't bought a plane ticket recently, then that could be suspicious and that would be detected as fraud. So let's actually view the machine learning process. Here we can see the main steps for the machine learning process, and we're going to go through each of these. So the first step is to actually get your data, and your data can come from a variety of sources. It really depends on your company and what your final goals are, but they can come from your customer data, physical sensors, and so on. And we also want to make sure that we have high quality data based off the data quality metrics that we discussed early on in the course. Once we've acquired our data, the next step is to actually clean our data. And these two steps, data acquisition and data cleaning, is actually typically where most of your time is spent, because this is probably the most important part of your pipeline. If you don't have good data acquisition and clean and formatted data, then you're not going to be able to perform very good analysis without having to go back and reacquire new data or clean the existing data you already have. So data cleaning is where we clean and format our data into standards that we understand. Again, things like making sure our data is structured in a way that the algorithm can understand it. So once we've cleaned and formatted our data, we will split the data. And this is a key part of the supervised learning process. This is known as a train test split. The reason we do this is because we want to be able to fairly evaluate our model. And the way we do this is we have our training data, which is going to be around 70% of our overall data. And then using that training data, just that 70% of our overall data, we take a specific machine learning algorithm and then train and build the model on that. And then once we've trained and fit that model on the training data, then it comes time to evaluate that model's performance. The reason we only use the training data for the model training is because we want a fair evaluation of the model's performance on data that it's never seen before. And that's why we have this separate 30% of our data as test data. So we take that model that we just trained on our training data, and then we evaluate it and test it on the test data that it's technically never seen before. And then here we can evaluate how well the model is doing based on the specific task and whatever specific evaluation metrics we're trying to learn about. And we'll discuss evaluation metrics later on in the course. But once we've tested our model, we can then go back and repeat the process and adjust hyperparameters of the specific model. Most machine learning algorithms have different hyperparameters that you can adjust. So again, the process is we split our data, we train the model on the training data, test the model's performance on the test data, and then keep adjusting onto the training data until we're finally satisfied with the test data performance, or we've decided that we can no longer improve our model. Once the model has been ready to go and it's set to release, then we deploy the model into the real world, either through some sort of internal application or some sort of external front-facing website. Again, it really depends on what the actual goal is and what we're trying to implement here. So classification and regression tasks are considered supervised learning processes. And later on, we're going to touch back on this process when discussing unsupervised learning methods such as clustering and dimensionality reduction, and discuss how it's different than the supervised learning technique. But for right now, let's go ahead and move along and learn about these two specific groupings of supervised learning. We'll start off with regression and then move on to classification. I'll see you there. Often, we have to predict continuous labeled data. Predicting continuous data calls for a know whether or not they have cancer. We're training our model and testing the results. So out of these 165 patients, if we're testing for the disease, actually some of them don't have the disease, and then some of them do have the disease. And then we're going to run those images through our model to have them predict, or have the model predict, whether or not these patients have the disease. So no, or a negative test, is it going to be equal to false or 0? And yes, a positive test, is it going to be equal to true or 1? So we have our little confusion matrix here, and this is the result of it being run on some test data. So the basic terminology we have here are true positives, true negatives, false positives, and false negatives. So again, we have this test data of 165 patients, and then we ran their images of, let's say, their moles on our actual trained model, and then we reported back whether or not we think they have the cancer or some sort of condition. So here, true negatives, that means that the patient did not have cancer, and our model predicted that they do not have cancer, otherwise a true negative. So true negatives here we have equal to 50. Then we have our false positives. That means that the patient doesn't actually have cancer. However, the model, when it saw the image of the mole, predicted that the patient did have cancer. So that's a false positive. It's falsely saying that I think it's positive for cancer. Then we have the patients that actually do have some sort of cancer and the cancerous mole on their skin, and the actual model predicted no. That's a false negative. So that's falsely saying they're negative for cancer. Then we have the patients that, again, actually do have cancer, and the model correctly predicts that they do have cancer. That's a true positive. So we can see here we have true positives, true negatives, false positives, and false negatives. So the accuracy, remember, that's just overall asking how often is the model correct. So you have true positives plus true negatives over the total. So our model here on this test set of 165 patients was 91% accurate. Then there's other metrics we can calculate, such as the misclassification rate or the error rate. Overall, how often is the model wrong? And it's essentially the reverse of the accuracy. So it's false positives plus false negatives divided by the total, or 9%. And that error rate is something you see reported as you perform Keras. So keep in mind, in certain situations, it's going to be really important to understand your false negatives and your false positives. For example, here we have a kind of high stakes problem where we're trying to tell patients whether or not they have a cancerous mole based off the image of their mole. That means we really want to try our best to reduce false negatives, because a false negative is essentially meaning that this person does have cancer, but our model is telling them not to worry, they don't have cancer. So that's an extremely dangerous position to put someone in. So you may want to trade off your precision versus your recall in order to help minimize your false negatives. Now, in that sort of same situation, false positives are also not really great, because now you're telling someone that doesn't have cancer that they do have cancer. But usually in the real world, there's further tests you can do in order to now test these people that have false positives. Maybe the next step is an actual biopsy of their mole. But again, we really want to try to reduce false negatives in that sort of high stakes situation, because we don't want someone walking away from our clinic thinking they're okay when in reality they are not okay. So keep that in mind. Different situations call for different importance on different metrics. And in our case, everything's pretty nice and low stakes because we're just dealing with images of cats and dogs, not something as important as detecting cancer. All right, if you're still a little confused on the confusion matrix, no pun intended, it's no problem. You can go ahead and check out the Wikipedia page for it. It has that diagram that we saw earlier, as well as all the formulas for all the metrics. And you can check out the different resource links I provided for you in this lecture for more breakdowns on precision versus recall versus accuracy. Welcome back, everyone. Let's go over some real-world applications for classification tasks. As always, we'll discuss some general real-world cases, things to keep in mind for your own classification problems, and a specific real-world case. So there's lots of different applications you could be using classification for. Some general real-world cases are things like medical diagnosis based off the features of some sort of biological matter. So often diseases use a lot of biological tests, and they want to classify you as having that disease or not having that disease. So what they can do is use that biological information, separate out that data into various features, and then classify the patient as having the disease or not having the disease. Things like loan approval is also based on historical customer information and features. So banks will take historical information, data on other customers who have had loans approved for them in the past, and then they look at things like defaulting rates, and they're able to then assess for new customers whether or not they should approve a loan. And even things like classifying spam versus ham or good email is a common case of classifying that you've seen pretty much every day that you use email. So things to keep in mind when you're working on your own classification problems are that the labels should be categorical, that is, distinct groups that you're trying to predict, such as has a disease or doesn't have a disease, or spam email versus ham email. Now, what you should also know is the correct labels for historical data in order to compare your predictions and evaluate the model performance. So classification, in this case, is always going to be supervised learning. Now, a real-world example can be something like the National Institute of Diabetes and Digestive and Kidney Diseases has developed a data set of physical and biological features of people, along with a corresponding label of presence of diabetes. So they have various physical and biological features, and then their label that they're able to predict is whether or not the person has diabetes. So then this data set has allowed for classification models to predict whether a person is at risk for diabetes based off their physical features, such as height, weight, blood tests, etc. So if you're interested in this particular data set, what you can do is you can actually Google the National Institute of Diabetes, Digestive and Kidney Diseases data set plus diabetes, and it should come up as one of the first top results in Google. Okay, thanks, and we'll see you at the next lecture. We've now reached our first unsupervised learning topic, clustering. Often, data won't have predefined historic labels. If this is the case, we will need to use an approach with unsupervised techniques in order to gain insight into the data. This section will discuss clustering techniques that allow us to take in unlabeled data and cluster it together into similar groups. An example of this would be taking unlabeled news articles and clustering them into similar topics, such as business, politics, or sports. Let's get started. I'll see you in the next lecture. Welcome back, everyone, to this discussion on clustering. We've already seen how to deal with labeled data, but what about unlabeled data? Often, you'll find yourself trying to create groups from data instead of trying to predict classes or values. You can think of clustering as an unsupervised technique that actually attempts to discover labels on its own when you have data with no historic labels. So this sort of problem in particular is known as clustering, and again, you can think of it as an attempt to create labels where you don't have any. You input some unlabeled data, and the unsupervised learning algorithm returns back possible clusters of the data, where each cluster can then represent a label group. This means you have data that only contains features, and you want to see if there are patterns in the data that would allow you to create groups or clusters. This is a key distinction from our previous supervised learning tasks and discussions, where we had historical labeled data. Now we will have unlabeled data and attempt to discover possible labels through clustering. By the nature of this problem, it can be difficult to evaluate the groups or clusters for correctness, because we don't actually have the correct historical labels. We're essentially just seeing what patterns there are in the data. So a large part of being able to interpret the clusters assigned comes down to domain knowledge in whatever particular data set you're working with. So maybe you have some customer data and then cluster them into distinct groups. It will be up to you to decide what these groups actually represent. Sometimes this is pretty easy, and other times it can be really, really hard. Again, it really depends on the data, what your answer or what question you're actually trying to answer, and what your domain experience is with the data itself. So for example, you could cluster tumors into two groups, hoping to separate them between benign tumors and malignant tumors. But there's no guarantee that the actual clustering algorithm will fall along those lines. It will just split up the data into the two most separable groups. Maybe it separates them on large tumors versus small tumors, or tumors with smooth geometries versus rough geometries. Again, the actual clustering algorithm won't tell you what the labels are. It's just going to tell you that cluster number 1 has really similar characteristics to each other, and cluster number 2, everything there has really similar characteristics to each other. So also depending on the clustering algorithm, it may be up to you to decide beforehand how many clusters you actually expect to create. A lot of clustering problems have no 100% correct approach or answer, and that's just the general nature of unsupervised learning, because it's not being supervised by any historical labels. Let's continue by discussing probably the most popular clustering algorithm, which is known as k-means clustering. K-means clustering is an unsupervised learning algorithm that will attempt to group similar clusters together in your data. So what does a typical clustering problem look like? Maybe you have a lot of text documentation that you want to cluster into similar groups, such as sports and politics and economic articles. Or maybe you have a lot of customer data and you want to cluster them based off their features to maybe try to implement different sales strategies per cluster, or do something like market segmentation, or identify similar physical groups for physical data. The overall goal is to divide data into distinct groups such that observations within each group are similar. So for example, on the left-hand side, we can maybe plot out our points along some X feature and some Y feature. Since we don't originally have labels, we can't color these based off some label. But after we apply k-means clustering, we may actually be able to then color by the groupings that k-means clustering observed. So we can see here that k-means clustering, if we asked it to give us the 5 clusters that are most similar to each other, it could discover those clusters that we colored over there on the right-hand side. The thing to note here is we have no way of knowing whether or not this is technically the correct answer because we never had the correct answer to begin with. So how does k-means algorithm actually work? Well, we first choose a number of clusters, and this is known as k. Then we randomly assign each point to a cluster. And until the clusters stop changing, we repeat the following steps. For each cluster, we compute the cluster centroid by taking the mean vector of points in the cluster, and then we assign each data point to the cluster for which the centroid is the closest. So let's see what this actually looks like. It's actually a pretty straightforward concept when we see it visually. We start off on that top left square where we see we have our data. So we have unlabeled data. And then step number 1 is to randomly assign each point to a particular cluster. And here, going from the data to step 1, we actually have to choose a k value. So we'll decide that we're going to look for 3 distinct clusters. So 3 colors here, green, yellow, and pink. So we have step 1, we randomly assign each point to the 3 clusters. Then on iteration 1, step 2a, what we end up doing is we randomly put in the centroids somewhere on top of these clusters. Then iteration 1, step 2b, what we end up doing is we look for every point and find the centroid it's closest to. So we can see here, those yellow points are closest to that yellow centroid, those pink points are closest to the pink centroid, and the green points are closest to the green centroid. And in iteration 2, step 2a, we move the centroid points over to the centers of all the points they've been assigned to. And then we're going to keep repeating that step over and over again until the centroids are no longer changing because no points are then being reassigned. And then we have the final results of our 3 distinct clusters. Now, keep in mind, we would have had to have chosen a k value before we even began this process. And that's really where domain experience and knowledge comes into play. If we take a look back at that older image, here we can see what the results of k-means clustering would look like dependent on what k value we chose. And you can see here that a lot of these k values actually seem really reasonable. For example, it wouldn't be unreasonable to just say k is equal to 2 and have those 4 little groupings as one category and then the red grouping as another category. Or it wouldn't be unreasonable to do something like k is equal to 5 over there on the top right, where we have each of those clusters on the left-hand side be its own little cluster, and then we have that larger group towards the top right be its own cluster. You can see here, we can keep expanding the k value. So the question is, how do we actually choose a k value if we don't have one in mind before we begin the clustering process? And there is no easy answer for choosing a best k value, but one way is the elbow method. First of all, we end up computing the sum of squared error, or SSE, for some values of k. For example, k is equal to 2, k is equal to 4, 6, 8, etc. So we repeat this clustering algorithm for different values of k, different numbers of clusters. And this sum of squared error is essentially a measure of how tightly things are clustered together. So the SSE is defined as the sum of the squared distance between each member of the cluster and its centroid. We can imagine that as k approaches the actual number of points we were trying to cluster together, then that error is going to get closer and closer to 0 because eventually we would have a centroid for every single point. But what happens is if we plot k against SSE, you're going to see that the error decreases as k gets larger, because when the number of clusters increases, they should be smaller, so the distortion is also going to be smaller. The idea of the elbow method is to choose the k at which the SSE decreases abruptly. And this produces what's known as an elbow effect in the graph. So you can see this in the following picture. Here we can see the number of clusters chosen for a particular data set and the within groups sum of squares. That is the actual error and how tightly packed these clusters are together. So choosing a k value off of this plot, what we're really looking for is a k value where choosing the next k up doesn't actually produce that much less error. So we are looking for that elbow point, and that seems to occur right around 6 clusters. So that would be a reasonable choice for this particular data set for k-means. But don't take this as a strict rule when choosing a k value. Again, a lot of it depends more on the context of the exact situation, such as your domain knowledge. All right, I hope you found some understanding here of the k-means clustering algorithm. We'll see you at the next lecture.
నుంచి ఫైల్ మిస్ అయింది. మన దగ్గర దేవుడి మీద కూడా ఫైల్స్ ఉన్నాయా? దేవుడి మీద లేవు కానీ మనకి ఒక దేవుడు ఉన్నాడు. టాకింగ్ అబౌట్ ఇండియాస్ బెస్ట్ kept secret, creator of Azad Hind Fauj, visionary and one and only Subhash Chandra Bose. But in 1945 లో ప్లేన్ క్రాష్ లో చనిపోయారు కదా. That's a government story. మన చరిత్ర నీ చేతుల్లో ఉంది. ఈ నిజం మన ప్రపంచానికి చెప్పాలి. Are you out of your mind? Trusted you. తెలియని విషయం చాలా ఉన్నాయి చెప్పు. Welcome to India's best kept secret. Yours, Subhash Chandra Bose.
ఏయ్, ఏం చేస్తున్నావురా పక్కన? ఏమన్నా ఫ్లాష్ చేసేవా పాటలు ఏమన్నా? కాపీరైట్ వచ్చి ఉంటుంది ఫ్లాష్ అయ్యంటే. అయితే మెసేజ్ ఉంటుంది అంటే ఏదేదో ఏంటో.
ఇచ్చినాను.
labels. So what we end up doing is we're grouping these clusters together within the data, and we don't actually really have a predictive outcome. That isn't to say we're going to be able to compare our predictions to the correct answer, because in this clustering process, we didn't have that correct answer to begin with. And a general real-world case that people really like to use clustering for is when you have highly dimensional data that is lots of different features in your data, and it's difficult to interpret directly just by seeing the raw data. So often when you're dealing with really highly dimensional data, and people like to do this with customer segmentation, what you can do is you can use clustering techniques to automatically segment your customer data. So the things to keep in mind is, as always, you're not going to know if clustering actually got the correct answer. And unsupervised learning in general, again, doesn't have the true labels to compare its results again. And that's really the main thing to keep in mind as you're performing clustering-based tasks. So a real-world application of clustering is the Google News feature. So Google News uses clustering-based techniques in conjunction with some natural language processing to deliver relevant news articles to users. And many articles online are actually not distinctly labeled sports, business, or finance, in particular with the way that Google is actually scraping the entire web for all of these news articles. It often won't get a nice label that will tell Google whether or not an article is on sports, business, finance, etc. So when first building Google News, engineers developed clustering-based techniques to actually cluster together similar news articles. So they were able to then, based off these clusters, have a little bit of manual reading and then decide what the cluster actually represented. The clustering technique wouldn't be able to report back whether a cluster of news articles represented sports or economics or politics, but it would be able to represent that the news articles themselves were very similar. And so that is able to then return similar results for whatever news article you're trying to find. And that really forms the basis of the Google News feature you see today. All right, thanks, and I'll see you at the next lecture. Welcome back. In our final discussion about unsupervised learning methods, we're going to learn about dimensionality reduction, specifically principal component analysis. Dimensionality reduction can help us with a variety of tasks, from data compression all the way to signal analysis. In this section, we're going to focus on principal component analysis and how we can use it to uncover hidden insights in our data that we wouldn't have been able to see otherwise. Let's get started. Welcome back, everyone. In this lecture, we're going to discuss dimensionality reduction, specifically how we can use principal component analysis to reduce the number of dimensions in a given data set. Dimensionality reduction allows us to reveal hidden insights from our data that we would otherwise not be able to immediately find. We'll discuss a method of this, as I mentioned, called principal component analysis, or PCA for short. So let's discuss the basic idea behind principal component analysis. It's an unsupervised statistical technique used to examine the interrelations among a set of variables in order to identify the underlying structure of those variables. It's also known sometimes as general factor analysis. Where regression determines a line of best fit to a dataset, factor analysis determines several orthogonal lines of best fit to the dataset. Orthogonal is just another word for at right angles, or perpendicular. So actually those lines are perpendicular to each other in an n-dimensional space, since we're often dealing with n-dimension data sets. And n-dimensional space is the variable in the sample space. So there are as many dimensions as there are variables. So in a data set with 4 features or 4 variables, the sample space would then be 4-dimensional. So let's go ahead and plot out some data. We went ahead and plotted it out along 2 features, x and y. And you can see here we have a regression line of best fit. So let's go ahead and add an orthogonal line to that regression line of best fit. And this will then allow us to begin to understand the components. Components are a linear transformation that chooses a variable system for the dataset such that the greatest variance of the dataset comes to lie on that first axis. So if we take a look at these 2 lines, you'll notice that the line that is similar to that best regression fit line that actually explains a lot of the variance in the data. So the data happens to have a lot of variance along that particular line. And then the second greatest variance happens along that second axis. So we can say that first line explains about 70% of that variation, and the second line explains about 28% of the variation. So note, with just these two lines, we're already explaining about 98% of the variation in our data set. We could keep adding more and more axes to try to keep explaining the extra 2%. But with just these two key components, or principal components, we're able to explain up to 98% of the variation in our data set. So note that the components themselves are uncorrelated, since in the sample space they are orthogonal to each other. So we could continue this analysis into higher dimensions and keep adding components, but typically you're going to be able to reduce a data set given just a few components. So if we take a look back at that similar example where we're plotting a bunch of data along a feature x1 and another feature x2 or y, we have these two key components which we can call C1 and C2. And we can see that if we actually plot the data points only along these key components, and maybe some other third key component, that we're able to reduce and explain a lot of the variance in our data set. So we no longer need all the features. So this is, I think, clearer when we're actually dealing with 3 dimensions. So here I have a bunch of data points plotted out in some 3-dimensional space. So I have 3 features in my data set, x1, x2, and x3. And I have these blue points in this 3-dimensional space. And what I'm going to do is I'm going to draw an imaginary plane, and that's the gray plane there. And I'm going to go ahead and mark the distance between the blue data point to my gray plane by that black line. And now let's go ahead and view just the plane itself. So here I have a new set of components, Z1 and Z2. Keep in mind, Z1 and Z2, those aren't original features of my data set. My original features were x1, x2, and x3. I've now used some sort of principal component analysis to reduce the number of dimensions from 3 dimensions, x1, x2, x3, to 2 dimensions, z1 and z2. And notice, we still get to see a lot of the variance of the behavior of the data set. This came at the cost of losing some information. And the information we lost is essentially this black line, the distance between that blue point to our imaginary plane. If we only see this imaginary plane, then we no longer have knowledge of that additional variance. But we can see that quite a bit of the variance is easily explained with these 2 components. And that's the main idea behind principal component analysis. It's being able to take combinations of your other features, create new components out of them, and still explain a lot of the variance in your data. And you can expand this to really complex examples. So here they're performing principal component analysis on some medical data. And you can see here that there's quite a complex mapping of this plane, but then once you flatten this out, you can see the separation between, for instance, these pink points versus these yellow points. And these happen to be data points for tumors. So if we use this technique on a data set with a large number of variables, we can compress the amount of explained variation to just a few components. And the most challenging part of PCA is being able to interpret those components, since they're really just a combination of all your other features. I'm going to hop over to a website called setosa.io, and I want to show you a visualization there that really shows you the power of why principal component analysis is useful. So let me hop over to my browser and show you this visualization. Okay, here I am at setosa.io. That's setosa.io, and I'm going to click here where it says explain visually. And once you click explain visually, there's lots of really cool visualizations here, and I'm going to click here on principal component analysis. So this is a visualization explanation of principal component analysis. It starts off with this 2-dimensional example where we see here our original data set plotted on x versus y. I'm going to zoom in here just one step further. And then you can adjust these points, and what's going to happen is over here we have the output from principal component analysis. We have these 2 components, PC1 and PC2. Now here we're actually not really reducing the dimensions because we're going from 2 dimensions to 2 principal components. So it's probably more useful with a 3D example. So here we can see through the examples. So we have these essentially 3 clusters along this 3-dimensional space. Now we can see here that it's calculated and plotted against PC1 or principal component 1 and PC2, principal component 2. And you can see if you actually view PC1 and PC2 over here that it shows you basically where these points lie. And based off these dark spots, you can tell that there's essentially kind of 2 main clusters around PC1 and separate 2 main clusters around PC2. So we can see the transformation using principal component analysis. Yet, I think for most people at this point, it's still not very clear why this would be useful. Why is it useful to view the data instead of its original feature space on this new principal component feature space? Well, let's go ahead and look at this real example. So here is an example of eating in the UK. So we have 17 dimensions of data for 4 different classes. We have England, Northern Ireland, Scotland, and Wales. And what we have here is the consumption of 17 different food groups, like alcoholic drinks, beverages, cereals, cheese, and so on. And it's been visualized using a count plot or bar plot of sorts. So we are already familiar with data visualization, and you may be thinking, well, data visualization is a good way of tackling these problems to see if there's any real difference between these 4 classes or these 4 geographical locations. However, if you take a look at just the visualization here, everything looks continue your studies in these topics. Best of luck on your journey through data science and machine learning, and thank you so much for taking the course.
Apa?
ఇంకా వేయలేదా కాయలు వేయి
Hello, welcome to this executive briefing course on data science and machine learning. This course is designed to be a high-level
Welcome to this course on artificial intelligence, the executive briefing. Artificial intelligence is disrupting the world, is disrupting industries and businesses, and this is your opportunity to get all the knowledge you need to be up to speed with the latest cutting edge technologies. In this course, we have 5 sections which cover 5 of the most disruptive technologies in artificial intelligence right now. And these are computer vision, natural language processing, reinforcement learning, deep learning, and robotics process automation, or RPA. Each section will start with a short introduction, then we will dive into specifics of that particular technology, usually between 2 and 3 videos. And finally, at the end of every single section, we will look at 10 use cases of that technology being applied in business to drive massive value already today. Here we are after the results, the real results, the numbers, so that we can get a feel for what each technology can do for our businesses. In total, each section is going to last about 30 minutes, so feel free to take them in your own time and space them out if you need, because these are quite advanced and disruptive technologies. So it's totally okay if you need to take some time to go through these sections. But by the end of this course, you will be totally up to speed with everything you need to know about artificial intelligence in order to incorporate it in your business and drive massive value add to your enterprise. Before we list various applications of computer vision, let's look at one specific example which will illustrate how easy it actually is to innovate with computer vision. This will give context for all other applications as well, so when you're going through them, you can already come up with similar examples in your mind that are relevant to your industry or company. The example we're going to look at is tomato sorting. Let's say that you are the CEO of a company that wholesales tomatoes to grocery stores. You want to make sure that your produce is of highest quality, and therefore on your conveyor belt, you have 3 people looking at the tomatoes and removing the unripe and rotten ones. Drawbacks of this approach are as follows. First of all, you need to pay 3 people to do this work all the time. Next is that humans make mistakes, therefore quality is not ideal. Drawback number 3 is that humans are slower than technology. Drawback number 4 is humans might get sick and not come to work, and this can cause the whole process to break down. Drawback number 5 is that this is not really enjoyable or creative work that these people really deserve to be doing. So now let's see how we could innovate with computer vision. What we would do is we would show a computer vision algorithm lots of labeled examples of good tomatoes and lots of examples of unripe and rotten tomatoes. In this case, you would be using deep learning type of computer vision algorithm. The good news is that you already have the labeled data. It's part of your process. You just need to set up a camera above the workers and let the algorithm watch their actions. It will see the tomatoes that go through, and those images will be classified as good to go. And it'll also see the tomatoes that get discarded, and those images will be classified as unripe or rotten. After a week or so of observations, the algorithm will have seen enough training data, and from then onwards, it can make the same decisions autonomously. All that's left to do is add a simple robotic mechanism that will knock out the rotten or unripe tomatoes. The advantages of this approach are as follows. Advantage number 1 is that costs are minimized. Number 2 is that errors are minimized. Number 3 is that speed is maximized. Number 4 is that there's no day offs or no sick days required. And number 5 is that humans can do more meaningful, creative, and enjoyable work. So that's one deep dive into one specific example. And next we're going to go through quite a few varying examples, use cases of computer vision. And it's important just to have similar images in your mind of how you might be able to apply those use cases in your business and industry. In this video, we will look at various applications of computer vision. All of these can be applied to images as well as videos, because videos are simply many frames following one another. Application number 1, image classification. It groups images into different categories and answers questions such as, is this an image of a dog or a cat? Is this an image of a defective or a working part? Application number 2, image segmentation. It partitions an image into multiple regions or pieces to be examined separately. For example, how Skype can blur out the background behind you on a call. Application number 3, object detection. Is there a pedestrian in this image or not? Is there a water spill on the grocery shop floor or not? Advanced object detection can actually recognize multiple objects in one image and draw boxes around them. Computers have actually surpassed humans in specific applications of object detection. For example, computers can now recognize dogs with 99.6% accuracy, whilst humans can only perform the same tasks with only 87.5% accuracy. Application number 4, object tracking. Where is this pedestrian going? Is that car traveling too fast? There's a recent example of when a Tesla car was able to apply brakes on a highway preemptively, meaning the brakes were actually applied split seconds before a collision happened in the same lane ahead of that vehicle. This is an example of object tracking in action, actually saving lives. Application number 5, image generation. You could transfer the style of one dress onto another. You could generate a 3D representation from 2D images. That's exactly how Google Maps does it when you go into the mode when you can see 3-dimensional images. Application number 6, edge detection. It identifies outside edges of an object or landscape to better identify what is in the image. Application number 7, face detection. What should the camera focus on? How many faces are in this image? That's how our phones can detect where our faces are in photos. Application number 8, facial recognition. This is the next step up and beyond facial detection, and it can identify specific individuals who should be tagged in this photo, for example. Application number 9, optical character recognition, or OCR. It recognizes words and numbers in scanned or even handwritten documents. Computers have gotten very good at this, achieving accuracy rates of over 99%. Application number 10, pattern detection. It recognizes repeated shapes, colors, and other visual indicators and images. Application number 11, feature matching. It is a type of pattern detection that matches similarities in images to help group them together. So there we go. Those were just 11 applications of computer vision that might be useful in your business. There's plenty more, but those are the main ones. And now is a good time to maybe pause this course and think about how some of these applications could be beneficial in your business and in your industry. In this video, we're going to look at 10 use cases of computer vision actually adding substantial value to companies already today. Use case number 1 is the Skanska company, which uses computer vision for worker placement. Construction is a worker-intensive field. Skanska, one of the largest construction companies in the world, determined that their workers walked an average of about 6 miles per day to get the right materials, tools, and equipment to the right place at the right time. Using computer vision to track their movement and compare it to their activity data, the company was able to optimize the entire building process, positioning workers, tools, and resources where and when they needed to be. This saved each worker about 2 miles walking every day, which in turn boosted the productivity of each worker by an hour every single day, roughly about a 12% increase. Use case number 2 is how Tesla uses computer vision in their self-driving cars. If you want to drive a car, you need to be able to sense your surroundings. And while hearing definitely plays a big part, the most important sense in driving is sight. Similarly, with self-driving experience. Since 2016, all the car to see its environment at centimeter precision. This move coincides with Tesla's massive growth in revenue, which grew by around 450% in the 3 years following the announcement. Use case number 3, Harvest CROO robotics, which uses computer vision to enable automatic crop harvesting. Even though we think of harvesting as a process done by huge machines, a lot of it is actually still done by hand. In Florida alone, 10 to 11,000 acres of strawberries are picked by hand every single year. It is predicted that the number of agriculture workers will reduce by 6% by 2024, so the need for automation is growing. Harvest CRO Robotics has developed a robot that uses computer vision to inspect strawberries, determine which ones are ripe, and pick them, all in 8 seconds per plant. One of these can harvest 8 acres per day, the equivalent of 30 human workers. Use case number 4, eBay and their image search capability. Consumers worldwide purchase around $3 trillion on the web every single year, with the 15 to 25% growth predicted to continue into the foreseeable future. Online retailers are coming up with new ways to improve the shopping experience and increase their revenue. A recent innovation is image search. If you see something you like, you can take a photo of it and upload it to find it on eBay. reduction in investigative volume of over 20%, as well as lowered their regulatory exposure by discovering new risk segments. Example number 6 is Deep Instinct and how they use deep learning for cybersecurity. Cybercrime costs the global economy $600 billion every year. Hackers are already using completely autonomous AI bots to try and find ways into systems in minutes rather than hours. And traditional security measures simply aren't keeping up. An unnamed Fortune 500 company installed Deep Instinct's deep learning powered security platform. Within the first week of deployment, the algorithm found 12 infected endpoints and with time found that almost 10% of their devices were infected, even though they had all been equipped with traditional security measures before. Despite requiring less than 1% of CPU usage, it tested 99% successful at finding and preventing incoming malware, including 140 cases of ransomware. Example number 7, Doxel and how they use deep learning for productivity tracking. Around 80% of construction projects are delivered over budget, with typical delivery times 20 months behind schedule. Part of the reason is that project managers lack a realistic instant visibility of the project's progress. Most progress tracking is still done with physical measurement, visual inspection, and clipboards. This is part of the reason why construction efficiency has only increased by around 1% during the last 20 years, whereas manufacturing efficiency almost doubled in the same period. Doxel uses deep learning to analyze data collected from robots and drones that traverse a construction site. This can detect deviations from the planned schedule and prompt the project team to act before delays start to pile up. During one project, labor productivity was increased by 38% and the project was delivered 11% under budget. Example number 8 is Amazon recognition and how Amazon uses deep learning in facial recognition. Although facial recognition is currently under scrutiny due to allegations of bias and concerns over individual safety, the technology is still in infant stages and experiencing fast development. It has numerous applications, and as a society, we will need to find out which ones of them are acceptable to us and which ones aren't. Washington County Jail Management uploaded all 300,000 mugshots they had previously taken since 2001 into the system. Later on, when a crime was captured on camera, rather than manually scanning the vast set of mugshots in the hopes of finding a match, recognition was able to find matches with 80% or 95% or even higher similarities. This has allowed law enforcement officers to quickly narrow their search and follow up on leads, often solving cases before any additional problems arose. Example number 9, Zestimate and how they use deep learning for real estate prices. The real estate market is the largest sector of the US economy, surpassing 30% of the total GDP. Opportunities as well as competition are vast, and real estate agencies are turning to artificial intelligence to handle them. The current shortage of appraisers has increased the time and cost of accurately predicting the price of a property. Zestimate uses a deep learning algorithm to analyze home characteristics, their unique features, and on and off market data to predict the price of almost 100 million homes in the US. Their median error for listed properties is only 1.9%, allowing real estate agencies who use their service to focus on customer acquisition and retention rather than costly and time-consuming appraisals. And finally, example number 10 is Zest Finance and how they use deep learning for loan approval. 7 million people in the US, around 5% of the auto lenders, are currently at least 3 months behind their car payments. This is powered both by customers that don't account for their own financial capabilities and by companies taking greater risks to try and improve their revenue. Zest Finance offers a deep learning algorithm that analyzes a potential customer's credit score and determines their risk of defaulting. This allowed a top US auto lender to cut its losses by 23% annually. So there we go. Those were 10 examples of deep learning in action, bringing tangible results to businesses already today. I hope this inspired some ideas of how you can use deep learning in your industry and in your business. Welcome to this executive briefing course on reinforcement learning. I appreciate that your time is valuable, and that's why in this course we will only cover the ultimate essentials for you to get up to speed with reinforcement learning and see tangible examples of how this technology can add substantial value to your business. Here's how this course is going to be structured. First, we will talk about what reinforcement learning is and why it has such a high potential to disrupt virtually any business and any industry. Then we will compare how reinforcement learning and human learning have fascinating similarities and what we can take away from them. Then we will discuss the 6 core advantages of reinforcement learning that make it one of the most cutting-edge technologies of today. Next, we will dive into 5 applications of reinforcement learning in marketing, a field that has benefited the most from these new technologies in the recent years. Finally, we'll look at 10 different case studies of reinforcement learning already being applied in different companies and industries. Here, we are after the real results, the numbers, so that we can get a feel for what reinforcement learning can do for our businesses in a tangible way. So I hope you're as excited as I am about the upcoming tutorials, and without further ado, let's dive into the world of reinforcement learning.
Times 20 months behind schedule. Part of the reason is that project managers lack a realistic instant visibility of the project's progress. Most progress tracking is still done with physical measurement, visual inspection, and clipboards. This is part of the reason why construction efficiency...
So what is reinforcement learning? Well, there are 3 main groups of algorithms in machine learning: unsupervised learning, supervised learning, and reinforcement learning. It can be very valuable to appreciate the differences between the 3. Unsupervised learning is used for discovery of new patterns. For example, clustering of customers into groups based on their similarities. The core principle here is that the resulting groups did not exist prior, but rather are suggested by the machine in the process. Supervised learning, on the other hand, is when we teach a machine to search and identify patterns that we have seen before. For example, classification of pictures of dogs and cats into the 2 categories, dogs and cats, is an example of a supervised learning algorithm in action. First, we show the algorithm thousands of already labeled images so it can extract the features that are essential to dogs and the features that are essential to cats. After this, the algorithm will be able to categorize new images as either dogs or as images of cats. The difference of this approach is to unsupervised learning is that we have to first provide labeled data for the algorithm to learn. Finally, reinforcement learning is something entirely different. Reinforcement learning is an area of machine learning where an imaginary agent, or the computer in our case, is being presented with a problem and is being rewarded with a +1 for finding a solution to the problem, or punished with a -1 for not finding a solution. Unlike with supervised learning, the agent is not given instructions on how to perform the task. Instead, it performs random actions and interacts with its environment. It learns through trial and error which actions are good and which actions are bad. An example of this is how robots learn to walk. Some robots are indeed pre-programmed how to walk. However, the more recent models master this skill through reinforcement learning. They don't have a preset if-else rule-based algorithm. Instead, they have a reward system built into them, which gives them a positive reward when they take a step forward, maintaining balance, and a negative reward when they fall over. That way, by exploring different possible actions that are available to it, the robot can learn how to walk forward. In fact, this method can not only teach robots how to walk, it can even teach robots how to play soccer. So that in a nutshell is what reinforcement learning is all about, and I hope you're super excited to explore this field further, because this is indeed the future of machine learning.
By companies taking greater risks to try and improve their revenue. Zest Finance offers a deep learning algorithm that analyzes a potential customer's credit score and determines their risk.
Reinforcement learning is surprisingly similar to real life. We humans use it all the time. Let's look at an example of a baby learning to walk. When it's starting to learn to walk and it falls over, it hurts itself and its nervous system sends a pain signal into the brain. Pain is a concept that is generated inside our body. It doesn't exist outside of our minds. It's nothing more than an electrical signal that's going into your brain. And so what happens is that the baby falls over and it understands that I'm experiencing pain, or subconsciously it feels pain, and therefore it learns not to do that action again. For instance, it was standing on its left leg and it raised its right foot towards its shoulder or something like that and made it fall over. And that pain signal is a reward, a negative reward for the baby's mind, for this baby's subconscious, not to ever do or try to avoid that action because it leads to pain. On the other hand, if the baby was able to make a few steps forward and grab a shiny object and it experienced joy, then joy in that case is a positive reward. It's a reward that is giving the baby positive reinforcement to continue doing more of those actions, and therefore the baby will learn that by doing those actions I get positive rewards, so I'll do more of them. That's how a baby learns to walk. Reinforcement learning is based on exactly the same principles, and because of that, because it is so similar to the way our own intelligence works, out of all the existing algorithms, reinforcement learning is the closest thing that we have gotten to in terms of true artificial intelligence. And that's very exciting. That's what we're going to be talking about in the upcoming tutorials.
Finally, we'll look at 10 different case studies of reinforcement learning already being applied in different companies and industries. Here, we are after the real results in numbers so that we can get a feel for what reinforcement learning can do for our businesses.
Recently, I interviewed John Langford, who works at Microsoft Research, and with over 50 published research papers is recognized as one of the world's leading researchers in the space of reinforcement learning. You can find this interview in episode number 275 of the Super Data Science podcast if you'd like to learn more. One of my most exciting takeaways from this conversation with John is that reinforcement learning is the future of machine learning. Why? Here's a quote from John. There are many situations where you just can't label data effectively. You have to learn from rewards. And since supervised learning relies on large labeled data sets, reinforcement learning has a much higher scope of application than any form of supervised learning. That was advantage number one, that reinforcement learning doesn't require large labeled data sets. It's a massive advantage because as the amount of data in the world grows, it becomes more and more costly to label it for all required applications. Here are some other advantages of reinforcement learning. Advantage number two is that it's innovative. Unlike reinforcement learning, supervised learning is actually imitating whoever provided the data for that algorithm. The algorithm can learn to do the task as well or better than the teacher, but can never learn a completely new approach to solving the problem. On the other hand, reinforcement learning algorithms can come up with entirely new solutions that were never even considered by humans. Advantage number three is bias resistance. If there's bias in the way the data is labeled, then a supervised learning algorithm will pick up that bias and inherit that bias. In this sense, reinforcement learning algorithms are better tools to find solutions free from bias or discrimination. Advantage number four is online learning. Reinforcement learning runs in real time. Reinforcement learning combines exploration, when the machine tests new approaches on the fly to find better solutions, and exploitation, when the machine exploits the best solutions which it has found thus far. This means that it can bring results while improving at the same time. Other algorithms will actually require retraining and redeployment in order to accomplish that. Reinforcement learning just keeps going. Advantage number five is that it's goal-oriented. Reinforcement learning can be used for sequences of actions. While supervised learning is mostly used in an input-output manner, reinforcement learning can be used for tasks with objectives, such as robots playing soccer, or self-driving cars getting to their destinations, or an algorithm maximizing return on investment on ad spend. And advantage number six is that reinforcement learning is adaptable. Unlike supervised learning algorithms, reinforcement learning doesn't require retraining because it adapts to new environments automatically on the fly. So there we go. Those were 6 advantages of reinforcement learning. Knowing these advantages can help you decide if reinforcement learning is the right tool for the artificial intelligence applications that you have in mind for your organization and your industry.
We humans use them all the time. Let's look at an example
walk and it falls over, it hurts itself and its nervous system sends a pain signal into the brain. Pain is a concept that is generated inside our body. It doesn't exist outside of our minds. It's nothing more than an electrical signal that's going into your brain. And so what happens is that the baby falls over and it understands that I'm experiencing pain, or subconsciously it feels pain, and therefore it learns not to do that action again. For instance, it was standing on its left leg and it raised its right foot towards its shoulder or something like that and made it fall over. And that pain signal is a reward, a negative reward for the baby's mind, the baby's subconscious, not to ever do or try to avoid that action because it's just pain. On the other hand, if the baby was able to take a few steps forward and grab a shiny object and experience joy, then joy in that case is a positive reward. It's a reward that is giving the baby positive reinforcement to continue doing more of those actions. And therefore, the baby will learn that by doing those actions, it gets a reward, so I'll do more. That's how the baby learns more. Reinforcement learning is based on exactly the same principles. And because of that, because it is so similar to the way how our intelligence works, out of all the existing algorithms, reinforcement learning is the closest thing that we have gotten to in terms of artificial intelligence. And that's very exciting. That's what you're going to get to know about in the upcoming tutorial. Microsoft research, and with over 50 published research papers, is recognized as one of the world's leading researchers in the space of reinforcement learning. You can find this interview in episode number 275 of the Security Sense podcast if you'd like to learn more. One of my most exciting takeaways from this conversation with John is that reinforcement learning is the future of machine learning. Why? Here's a quote from John. There are many situations where you just can't label data effectively. You have to learn problems. And since supervised learning relies on large labeled data sets, reinforcement learning has a much higher scale of application than any form of supervised learning. That was advantage number one. That reinforcement learning doesn't require large labeled data sets. This is a massive advantage because as the amount of data that there grows, it becomes more and more costly to layer into Here are some other advantages of reinforcement learning. Advantage number two is that it's innovative. Unlike reinforcement learning, supervised learning is actually imitating whoever provided the data for that algorithm. The algorithm can learn to do the task as well or better than the teacher, but can never learn a completely new approach to solve the problem. On the other hand, reinforcement learning algorithms can come up with entirely new solutions that were never even considered. Another sort of thing is bias resistance. If there's bias in the way the data is labeled, then a supervised learning algorithm will pick up that bias and learn inherent bias. In this sense, reinforcement learning algorithms are better tools to find solutions free from bias or discrimination. Advantage number four is online learning. Reinforcement learning runs in real time. Reinforcement learning provides exploration when the machine tests new approaches on the fly to find new solutions, and exploitation when the machine exploits the best solution which the machine has found thus far. This means that it can bring results while improving at the same time. Other algorithms will actually require retraining even though they learn to reinforcement learning. Number five is that it's goal oriented. Reinforcement learning can reduce error sequences of actions
quick fixture. MLS, mega mega raw shout out. Mega mega love shout out. Machine learning from పడుకునేసింది. నీ దాంట్లో ఇది ఎట్లా వేసుకుంటుందా? ఇది ఎట్లా వేసుకునేది? ఎట్లా నీ దాంట్లో ఇది ఎట్లా వేస్తావా?
ఎట్లదే
నేను చూపిస్తాను. యూట్యూబ్లో పైన డీప్లు ఉంటాయి కదా, అందులో అది ఎట్లా వేసుకుంటారో ఇట్లా కదా, ఇట్లా చెప్పిన
ఇట్లా అందరి అందరి వస్తాయి, మామూలుగా వస్తాయి అదే
మామూలుగా
ఆటోమేటిక్గా వస్తుంది, ఆటోమేటిక్గా వస్తాయి. మ్యూట్ చేయడం కదండి, మ్యూట్ చేయడం.